All right, and so now when it comes to the trig substitution, doing a trig substitution, there are actually more than one way of doing trig substitution. So now after you have seen how we have done some trig substitution based on substituting our variable with a sine function or a cosine function, then allow me to introduce another way of doing a trig substitution right here. So as a matter of fact, now if we're looking back at the title of our discussion of our lecture here, then it should be trig substitutions, because there are multiple ways of doing a trig substitution. Okay, so now allow me to introduce that style, that new style. So I'm going to promote the following problem here. So let me now introduce, so here we want to evaluate. Okay, so this is not an example, but this is where we are promoting a new problem right here, a new kind of problem, where let's see we can explore a new way of doing substitution. So how about I'm having a square root of 4 plus x squared. Okay, so it's another indefinite integral problem that we want to look for a way to find that answer right here. So an indefinite integral problem, at this point in your learning, it is an antiderivative. So what function has this? The square root of 4 plus x squared as its derivative. Okay, and so, and this inside the square root here, it's a 4 plus x squared, or you can think of that as an x squared plus 4. It should be the same way, but basically it's an irreducible quadratic here. That's one observation. Okay, and then further I'm seeing this. It's just an observation before I formally get into the problem, but I see 4 here can be understood as 2 squared. Okay, 4 is the same as 2 squared, so that means the 4 plus x squared inside of our square root can be regarded as a 2 squared plus an x squared. So what I'm seeing here is basically we're looking at a constant term that can be expressed as a square of a number. So a constant term and plus, okay, plus. So unlike the earlier style of unlike the earlier case where I was showing the previous substitution style for trig substitution, then here we're actually having a constant, which again can be expressed as a square of a number, but then it's that constant term plus an expression square, and we will get to that generalization later as well. Okay, but for now in this problem here, as the way it is, then we have 2 squared plus, right, x squared right here. So here's our variable square, and this is our constant term expressed as a square. So now in that way, since you have already had a little bit of experience that we were doing with trig substitution earlier, the one with the sine of theta over here. So now I am going to, and believe me to introduce, allow me to introduce this. I'm going to substitute x, the x variable in our expression here, in our function here, by 2 times tangent. So instead of sine, like I did in the earlier case, instead of sine, x equals a times sine of theta, like all of those problems we did in example 1. Here I'm substituting x equal 2 times tangent. So I'm using tangent here this time, primarily as the style here. Okay, and then if you start recognizing some pattern or already hold that for yourself, be patient and follow along with my video lesson here. But this 2 here really came out from what we recognized earlier as 4 is the same as 2 squared. So this 2 right here is what I used in that formula here, in that substitution choice. All right, so now once we were doing that, then just like that same experience how I have done when we were substituting the variable with the sine function, and here I can see that if x equals 2 times tangent of theta, then that means tangent of theta has to equal x over 2. That's one thing. Okay, and we can also see that and from that way I can also see that taking the derivative dx d theta has to equal, so now it's 2 times so the derivative for tangent is secant square of theta. Okay, so dx d theta, we're taking the derivative, treating x here, and so just all that understanding we've had previously from doing the sine substitution is here, even though here we're using a substitution as the tangent theta. Okay, so dx d theta is 2 times secant squared of theta, because secant square is the derivative for tangent. Okay, but now just like that, this symbol for derivative is also understood as a quotient or as a ratio of two differential dx and d theta at this point of your learning in calculus. And so in that way, I can go ahead and multiply the d theta to the other side. That leaves me dx to be equal with the expression 2 times secant squared of theta times d theta, okay, times d theta. And so now we are ready for finalizing our substitution. And what I mean, we're ready for bringing all of these substitutions into our problem, piece by piece. So with the starting function here, okay, and we're still just turning around with the expression. We still didn't take the antiderivative yet. We still didn't take the indefinite integral yet. So that symbol remains the same. Square root is here. Now I have 4 plus, but x, the x squared now, but x itself is substituted by 2 times tangent theta. So that means x squared here will become 2 times tangent theta all squared. Okay, and that's all that here is taking place inside of our square root. And then the dx right here, now we also have derived for ourselves a substitution expression for that. 2 times secant squared of theta, d theta, is to be substituted into dx right here, for dx right here. So now I'm looking at 2 times secant squared of theta with a d theta. Okay, so that's, so once again, as far as connecting our understanding here with the major fundamental in the concept of substitution method here, we have to check ourselves, have we completely washed away the old variable? Okay, the old variable meaning the x variable, have we washed that away completely? Yes, we have. Okay, so this is a completely brand new integral in terms of the new variable, theta. And so just like I said in the very beginning of this lecture right here, when we started getting into doing a trig substitution, I was saying earlier that trig substitution really is an extension or an extended style of doing substitution problem. Okay, but it has its own specialty, so it needs to be taught as a separate lecture right there. All right, so now I'm gonna at this point we're gonna have a couple advantage of doing that. We still didn't find the antiderivative yet, so I'm going to leave that symbol here, but we can do something more with that. So the square inside the square root, so 2 times tangent all square is the same as 4 times tangent square. So we're looking at now a square root of 4 plus 4 times tangent square. Okay, that's just the algebra multiplied with 2 times. And now allow me to actually bring that 2 here from the previous step to the front, because that now exists only as a constant coefficient. So in the rule of taking antiderivative or indefinite integral, we can bring that constant coefficient to the front. So now I'm going to write that as so I'm going to have a little bit of a tight space here, but it's 2 times. Okay, so 2 times the square root expression, and now with the d theta. Okay, so now, and I'm missing the secant square theta, d theta. Okay, and so now inside of the square root, I can even have a little more work around right here. I can factor out that common factor 4. So factoring it out, it's going to give me 4 times 1 plus tangent squared. That's how we factor it out. Okay, and then that 4 here, since being in product with 1 plus tangent squared, I can pull it outside of the square root. So allow me to speed up the process a little bit. So think about this square root right here that contains the expression, but having 4 factor out, now I can also in the next step pull the 4 outside of the square root, turning it into a 2. So algebraically, our square root expression in the next step becomes 2 times square root. Now inside of that, we're looking at 1 plus tangent square of theta. Okay, and then that multiply with secant square of theta with the d theta. Okay, so we keep making our integral problem shorter and shorter. We keep simplifying it. So thanks to this trig substitution right here, we are able to keep reducing our expression simpler and simpler, and then keep moving on right here, and we will find a way. But now, before I move on to the next step on my other board, so you can see that we produce for ourselves another constant coefficient, which can be brought in front again, and together compensate and together multiply with that 2 that's already there in front of the integral. And so now on my other board. All right, so here's what I see for the next step. It should be 4 times the integral, and now I'm looking at 1 plus tangent square theta times, now this secant square theta is outside of the root, and then the d theta. Okay, so now a quick little reminder. At this point, I need viewers and students of mine who are studying with me to pay attention to this 1 plus tangent square of theta right here. So 1 plus tangent square of theta, according to according to those famous Pythagorean identities in trigonometry, then 1 plus tangent square of any angle theta will equal to secant square of the angle. Okay, so that all comes from, any of this comes from the Pythagorean. I mean, in my years of teaching the trig and calculus, especially in trigonometry, Pythagorean identities is a whole family of identities where it all came out from the Pythagorean the theorems right there. So this is one among the Pythagorean identities right here. So this is a brief review. So 1 plus tangent square equals secant square. All right, so I can use that result in this part right here. So 1 plus tangent square inside my square root right here, I can write that as, so now in my next integral, it's a square root of secant square. Okay, and then times an extra secant square. All right, so now square root of secant square will reduce down to just a secant and multiply together with the secant square outside of the root. Now our next step here will show, and it's shortened enough, so I'm gonna just write it in the same line right here. We're looking at an integral as following: 4 times the integral of secant cube theta d theta. And so now we came down to that. So this is a very simple integral, but it's in the form of a power of one single trig function, secant. So cube or secant cube of theta. Okay, secant cube of theta, that one single function, one simple function, but one single power of a trig function. Okay, high power, like power 2, power 3, and so on and so on. So now, again, recall, we have seen earlier, I brought this up back in the days that we were doing the integration by parts, but we have proven at some point before this lecture right here, we have proven that this reduction formula right here, or at least I have brought up to my students' attention that there is a reduction formula for our secant function. So generally, if secant is raised to a power n right here, so in this case, guess what? It looks like our problem here, n has to equal 3. So this is n equals 3. Okay. So my point now is that we can use that power reduction formula to get this integral done right here. So let's one more time have a closer look at that power reduction formula. And then feel free to pause the video to copy down the formula so that you can have a clear understanding of how I'm applying this. All right, so here's the power reduction formula over here, and it looks not that complicated. It looks quite clear in the way how it's being setting up. Okay, and so it's just one among the many other reduction formulas for trig function. So now clearly recognizing that our n in this power form right here, in this power reduction formula we're about to use is n equals 3 at start. And so now I am going to use, so I'm going to put the 4 here as a common coefficient. Okay, and then now it's going to be 1 over now n minus 1, which is giving me just simply a 1/2. Okay, so, and I don't think I need that gigantic fraction bar, so it's just 1/2. Now I'm going to go secant, okay, and the formula set earlier, as you have seen, that secant to the n minus 2, so this is now going to be just n minus 2, n is 3, so n minus 2 is just secant of theta, power 1. All right, and then we have to, according to the formula, multiply with tangent theta. But this part right here is the part that's already being done with the integral. Okay, and so now, we produce first term 1/2 times secant theta tangent theta. Okay, and then I'm going to need to add, and then the reduction formula says we have to produce, according to the formula, n minus 2, which is 1 again, okay, and divided by n minus 1, which is 2. So it's another 1/2 here, and multiply, but now it's secant of, so n is 3, but n minus 2 in our formula, it's just the way it is. So now secant of theta d theta. So we produce for ourselves another integral, okay, but with a much lower, about 2 steps lower power of secant here. And that's how I used my power reduction formula for secant. So now, at least it's giving us light here, because this one here, well, it's at least easier. It has a way for us to handle. So now, but before I get into the next step, I'm going to go ahead and multiply and distribute that 4 into each term here, including that term that's still being as an integral here. So now, I want to save that space for my next step. So here, just simply distributing out the 4 allow me to do this dirty trick. So 4 multiplied with 1/2 will become just 2, okay? And then 4 multiply, and we have no worries about sign change because the 4 in front was a positive constant. And so multiplying 4 with a 1/2 here will give me just 2. So now it's more laid out for us. Okay, and so now that first term is done. We only have that small little integral to handle. And it's a 2 times secant of theta. So now I'm going to rewrite the first term here in the way it is. 2 times secant of theta times tangent theta plus 2. And now we have learned previously. Okay. I had video lessons of mine earlier as well, as there are many video lessons over the web that shows, and you can find even a formula for this, secant of theta as a common formula throughout many standard calculus textbooks. So you have a lot of resource about this, even my own video showing how, or the other people's videos being posted over the web, or even the many textbooks include a formula for secant, a quick formula for secant of theta right here. So there's no need to show the work how it's done. But antiderivative, now the 2 is here. Antiderivative, or the indefinite integral for secant of theta, is simply just the natural log, okay, the natural log of secant of theta plus tangent of theta. Okay, and we're putting that in absolute value. Okay, all right. So we're putting all that in absolute value. So now, after we have looked at that, and like I said, I have my own video showing how secant indefinite integral of secant theta becomes this, or there are many other people's videos being posted over the web. Look at all of those to learn from different experience, same problem, but being looked at from different angles. And then there's also, of course, the formula anywhere in any of the standard calculus textbooks to show the formula to go from secant theta down to that final formula. Okay, and then here we have to add c. So really, I'm going to now go ahead and multiply 2 with the natural log expression here. That leaves me really 2 times natural log. So the only way I ask you to pay a little attention that the secant theta plus tangent theta right here must be inside the absolute value. Okay, so it's just the way how it is. Anytime you take the antiderivative or you take the indefinite integral and your answer has to come out being a logarithm, then we have to put that in absolute value to ensure that the arguments inside the logarithm here has to be a positive quantity. It's the way how we're working with logarithm operation in our math right here, in our kind of math. Okay, as long as we are human on earth, we will always have to stick with positive values for logarithm. It's the way it is. All right, so now in that way, we thought, for one instance, we thought we're done with the problem, but we're not quite, okay? We're not quite done with the problem in the sense that our final answer here, we're done with taking the antiderivative, but our final answer cannot be in terms of theta as current point right here. So we need to find our way to bring back the x variable, because our problem started out in the beginning was a problem in terms of x. Okay, and so now let's spend some time doing some understanding right here. So I still have the substitution work right here, my sketch of the substitution. Every information regarding the substitution for this problem is still retained here. So what I see, tangent of x equals x over 2. So just that similar style that I've been doing with the earlier trig substitution that we've learned, we have to put this on a triangle. So let's assume, when I gave that definition, x equals 2 times tangent theta, then I was defining that in in the requirement that the angle theta has to be anywhere from minus pi over 2 to pi over 2. Okay. All right, so we have that requirement. And so now, and we're going to assume that the tangent theta here is going to be, the theta is going to be in the region where it produces the positive tangent. So now, think about a triangle. Okay, think about a triangle. All right. And aside from that, and you have seen this argument I've made before, but it doesn't hurt to repeat. Outside of that, or aside from that right angle here, then you can imagine that we can place our theta angle anywhere in any one of these two vertices. That's aside from this right angle. So as a choice, I put my theta here. So this is opposite from theta. This side right here is opposite. This side is adjacent, and this side is hypotenuse. So tangent is famously known within a triangle, within a trig triangle. Or trigonometry in a triangle over here. Then in a right triangle, then tangent of theta is opposite over adjacent, opposite over adjacent. And currently we know that tangent of theta is equal to x over 2. So that means this is adjacent, this is opposite. So I have to put my x on the opposite edge right here, and put my 2 on the adjacent side. So that means the hypotenuse here has to come out, according to a Pythagorean theorem, square root of 2 square plus x square. That's how we have been calculating length in a right triangle. Okay, so in that way, so that means in that way. So first of all, so I know how to express tangent of theta as in terms of x. It's an x over 2. Okay, but our function here, our final antiderivative at this current point also involves some secant of theta. Okay, it has some secant of theta involved here, and so I am going to swing back to this board, and let's find out how we can express secant of theta in terms of the x variable. So secant is 1 over cosine. 1 over cosine, or the reverse, the reciprocal of cosine. 1 over cosine. So cosine at start, cosine is adjacent over hypotenuse. But now secant is the reciprocal. So that means we're going hypotenuse over adjacent. That's secant of theta. So hypotenuse is the square root of 2 square plus x squared. That's a hypotenuse, and divided by 2 over here, the adjacent. So that's how we define secant theta. That's how we understand about secant of theta in a right triangle. Okay, from a right triangle setting right here. So now we have that expression of x in terms of x that can be substituted for secant of theta. And so now we got tangent of theta expressed as a function of x. We now have secant of theta expressed as in terms of x. So now we are ready to bring back our expression right here. All right, so I just now modified the space here a little bit to leave myself enough space down here. But so secant of theta from our previous step, it gives me square root of 4 plus x squared over 2, all over 2. And then that same expression here, we need to multiply with x over 2. That's our tangent. Okay, so that's multiplied with x over 2. And now I'm going to add 2 times natural log, and then again, secant of theta, I'm looking at square root of 4 plus x squared over 2, and then plus x over 2. Okay, and plus c. All right. And so at this point, we're almost done. The reason I'm only saying we're almost done because I want to show students the way to simplify this down even a little further, because there's still about a 30% chance that your instructors are out there, outside of myself teaching right here, there are about 30% of instructors who do not allow students to leave the answer without simplifying. Okay, and so let's spend some time simplifying this. We can cancel out a 2. We can cancel out a 2. Okay, and then put that together in a one expression here, and we can also simplify this logarithm expression a little bit more. Okay, so now I am going to erase this part of my board here. And I'm only leaving that last two steps there. So now with this expression, after we have cleared out one of the factor 2 over here, and with that x over 2, now I'm looking at first term being x times square root of 4 plus x squared over 2. That's how short it will become. Okay, and plus, now it has to be 2 natural log of, see, the good news is that the two terms in our natural log expression here has a common denominator. So I can write that as one. I can write it in one expression right here over 2, and then here we're looking at square root of x square root of 4 plus x squared plus x in the numerator and plus c. Okay, but I'm still not quite happy, and I'm purposely doing this to get you more to give you more flexible experience with the constant c later on, and you will see my point later on. Okay, but logarithm, right now logarithm here is a logarithm of a quotient. So anytime we're taking logarithm of a quotient, we can do the following. Yes, admittedly the first term stays the same, nothing else can be changed in that. So I'm going to write it there, x times square root of x squared all over 2. That's the first term. Okay. But then plus 2, now like I emphasized just earlier, this is a logarithm of a quotient. So property of logarithm, see, logarithm of a quotient, a over b is the same as logarithm of a minus the logarithm of b right there. So we can produce a logarithm of a quotient into a difference of two logarithms, same base. Okay, and so in that way, here's how I'm seeing it. This is 2, okay, times a logarithm of the square root of 4 plus x squared plus x. That's one of them. And I had that 2 here simply because of that common factor. Okay, and then minus 2, that same 2 is distributed in, times logarithm of 2. Okay, and plus c. Okay, so that's how I broke it down so far. But I want students of mine or viewers who are learning from me right here to see this. In the end, the minus 2 natural log of 2 here is a constant as well. It's a constant additionally being added on top of that plus c. So in the end, that's why you see this throughout many textbooks in calculus. They're going to skip this part right here because they include that minus 2 natural log of 2 together with that c. Recall from our understanding of the c when we first learned about taking antiderivative, the c here simply represents a constant. But it doesn't matter what constant that is. So we can include together this. We can include this minus 2 natural log of 2 together with that c as a different c. So that's why now all together here we actually arrive as our final answer being just one c right here. It's maybe let's call it a c1 to make it for this problem a little bit different with the other c right here. But in the end, they are just constant terms. So this is our final answer. This is the antiderivative or the indefinite integral for our starting problem. Our starting problem was the integral of square root of 4 plus x squared. It's a simple problem. The starting problem looks short, but now surprisingly it took us into such a lengthy final expression for antiderivative. But hey, in the end we're done, and that method that we substituted x by 2 times tangent theta. That made the problem working. Okay, and so this 2 here, again in my explanation, this 2 came out from because we recognize this 4 here as a 2 square. All right, so now admittedly at this point we're done with this problem, but allow me to bring up some generality about this problem before we actually hit into some examples so that you can see a solid generality right here. Just like how I did that with when we were doing the substitution using the sine function. Okay, so here's how I see it. This problem is a very basic problem that I brought up, but it primarily has this form right here. That at least what I can see here is our integral here contains, this integral only has this square root with a 4 plus x squared, but I'm talking about generally out there. What I see here is that we have a constant term expressed as a square, a constant term expressed as a square, and plus with an x squared here. Okay, so this function here, we're doing it is obviously having that, but there could be other functions out there having even more things involved than this. But at least as long as we recognize our function that we're trying to take the indefinite integral for, if we recognize our function has this component being part of that function, then we can start taking the trig substitution using the variable, to let the main variable in our expression, in our problem, to equal 2 times, equal a times. So x here can equal a. See that constant before the square, a times tangent of theta. That's the generality right there. And of course, we are doing this substitution under the requirements that theta should be an angle anywhere from pi minus 2, negative pi over 2, okay, not pi minus 2, negative pi over 2, and to positive pi over 2 right there. All right, but then I also want to point out, because we will get to that kind of problem sooner or later, but the intention here is that in this generality I'm pointing out is that the x here is not simply understood as just one single variable. Yes, it's good to understand that way at start, but in the end, I want viewers or students who are learning from me to have a broader understanding that the x squared here, the square term here, out aside from that constant. This is constant, so nothing to be done with that. Okay, nothing else we can argue about that. But this x squared here, it's a variable. So think of that. It could also be a squared plus some expression. That's why I'm using big capital X right here, squared. So anytime that it's that same generality right here. Anytime we're looking at a constant term plus, what needs to be highlighted here is the plus existing between the constant term, right, and the expression being squared. So now I'd rather see this as just some expression, some variable expression being squared. Not necessarily only one single variable. That's the easy case, but I'm talking about more generally as a broader understanding. Okay, to expand your generality right there. Then the square term, the other square terms can also be just more than a single x variable. It could be an expression, a variable expression square, and then in that way we can always use. So x here is a variable, some variable expression, not just a variable. Okay, so that's what the capital X is. Then in that case we can still take that variable expression right there to substitute by a times tangent theta. I'm talking about a times tangent theta, that a. All right, so that's a larger generality of the sort of like the extended case of this form right here. That rings a sign for us, rings a bell for us that we should use the substitution as following. And then you have seen all of that substitution work, learning from my work I've done earlier. Okay. All right. So now we are ready for example 2. So let's look at now formally example 2. So, and you can see that throughout example 1 that we have done earlier, the entire example 1 was all about the entire example 1s throughout all different little problems of A, B, and C right there. They're all about we're applying that trig substitution with letting the variable or the variable expression equals a times sine of theta. Okay, and so now you can see that in my style every example is one class of problems. So here I'm going to specifically introduce those problems where we're going to use the expression to be substituted by a times tangent of theta. Okay, so that's the plan. So here we go. Here's the first problem, part A in the example here. So let's look at what it is here. How about an integral, okay, of 1 over, and here we have x squared times the square root of x squared plus 16. Okay, so, and with the dx. All right, so just like that, right here I recognize we have a square root form just like that generality I pointed out, right? That we have a square root, and inside of the square root we got the form a constant term plus with a square expression. And that gladly that square expression is only one single variable here, not like a variable expression. We may or we may not get into that actual problem where the square here is an expression, is a variable expression. But for now, let's stay with what it is. Right there. So I noticed that. So simply I noticed that this is just something to notice. Okay, and then shortly I'm going to erase that. The x squared plus 16 inside the square root here can be understood as x squared plus 4 squared. So now it's making it even more obvious that this is our a. That when we substitute, we're going to put that in front of the tangent. But clearly we have to use a tangent theta. Okay, so x squared plus 4 squared. So a little bit unlike the introduction in the introductory example that I did earlier, was that here I put the x squared first, but see, addition is completely commutative, so we can switch around the order of addition. Okay, so now it is apparently that I am going to substitute x by 2 times, and actually I have to correct that, 4 times tangent of theta, under that requirement that theta has to be an angle anywhere from minus pi over 2 to pi over 2. But this information is usually not directly applicable to our work here at the Calc 2 level right here. Okay, so from that we understand now that x over 4 must be equal to tangent of theta. We found for ourselves another substitution point right there. Okay, another point for later on, useful for later on. But then right from here, if x equals 4 tangent theta, then that means dx d theta, taking the derivative of our function x in terms of theta, gives me 4 times secant squared of theta. Okay, and again, just like how I explained many times now up to this point in this lecture right here, we can, aside from seeing this as a notation for derivative, we also see this as a ratio of two differential expressions, dx and d theta. And so we've seen this idea at the end of our calculus 1/4, or we have seen, in case you haven't seen that in your Calc 1 level, then you also have seen that as a reveal prior to the day that we learned, prior to the lecture that we learned about the substitution methods. So, but now all my point now is that seeing this as a quotient of differential expressions, I can now multiply the d theta to the other side. So dx we equal 4 times secant squared theta d theta. Okay, so we have now just enough useful information to start putting these pieces in place right here. So now I'm seeing, now this is how I see I can do the substitution for my problem right here. It's a 1 over, and I'm just doing the substitution. This is nothing to do with the antiderivative yet, okay? And so 1 over, see, x squared, x is defined as 4 times tangent theta. So x squared, that x squared in the denominator is really 4 times tangent square, okay? So we're looking at 4 times tangent square of theta, and then multiply, so I need to extend my fraction bars here. Square root of 4 times tangent square theta plus 16. And I'm lying already. This is supposedly 16 because 4 also gets squared out. Our x equals 4 tangent square of theta. So it needs to be 16 tangent square of theta. Allow me to go a little brief in the little algebra steps like that. Okay, and then plus 16. All right, so that's, it looks a little lengthy here at this point, but it will get shorter. And then the dx here can be substituted by 4 secant square theta. Okay, and with the d theta. So here it's going to be, now so to keep the, I have had that video lesson that clarifies, but a lot of time we can also put, so the dx here is in the end is all means timing, or being in products with the fraction here. So I can put the dx here on top, and that turning it into a 4 secant square theta d theta. It's all about, you know, saving space purpose right there. Okay, and so now, or you know, to still keep it clear, I can still put the theta here. I have enough space for that. Okay, so now we can do a little more about this. Okay, so I can see that 16 will cancel with 4. 16 will cancel with 4. Okay, and it leaves me a 1/4 in front. Okay, and then in the meanwhile, now I have tangent square of theta plus. Now the 16 here in the square root can also be factored. So now it's a square root of 16 times 1 plus tangent square theta inside the root. Okay, and all of that there is multiplied with a d theta. Okay, so we have only one single secant square on top. Okay, secant square of theta on top of our numerator. Okay, on our numerator. And so now the 16 in this product here inside the square root can even be factored further into the, can be pulled out of the root. That's what I meant. And then pulling it out from the root, it becomes 4, and then we can pull it out in front. So that's making it, in my next step, 1/16, because see, that becomes a 4 here after pulling it out of the square root, and then we can pull it out. So multiply together with 1/4, it gives me 1/16. And here we're looking at the integral, and now I have tangent square of theta in the denominator times square root of 1 plus tangent square of theta. And then there's a secant square of theta on top right here with a d theta. Okay, and so now we keep getting our expression keeps breaking down and looking simpler and simpler. Okay, so it's high hope that there's a finish point. Okay, and so now on my board here, on my other board here, then I'm gonna continue with the next step. So it's a 1/16. Okay, and the integral here we got secant squared of theta on top. Here we got tangent square in the denominator. Okay, and we have that square root. So now that square root there becomes square root of secant squared of theta. Okay, and then with the d theta. Because remind yourself, 1 plus tangent square of any angle theta will equal secant square of theta. I also reminded anyone about this when I was introducing that promoting example earlier. So that's how I substitute the 1 plus tangent square inside my square root of that earlier step to become the secant square inside the square root at the denominator. And that's how I had this. Okay, so now in my next step, again, there's a 1/16. Okay, as an integral. Now we have secant square of theta, and I'm dividing that by. So this is here after reducing the secant square right there with the square root. I'm looking at tangent square, okay, times secant of theta, d theta. And so the secant here will cancel with that. The secant square will cancel with that. Okay, the secant square will cancel with that, and then eventually it's gonna give me something shorter. It keeps breaking down, so it's 1/16 times the integral of secant theta over tangent square theta. Okay, times tangent square of theta d theta. All right, tangent square of theta d theta. Okay, so we need to, when it comes to something like this, then we need to see through the trigonometry functions a little bit. So you got to review your algebra on the trig functions. Okay, you got to know the algebra on your trig functions. So secant divided by secant theta divided by tangent square theta. I can just simply remind anyone about this right here. Secant of theta divided by tangent square theta can be simplified down to, okay, cosecant theta times cotangent theta. I want students of mine and viewers to write this down, and I want you to do your own proof, because like I said, at this point, taking a calculus class, you should be able to derive this. So I want viewers or students of mine to verify on your own how I set this, to verify the validity of this identity right here. And I'm telling you, secant of theta over tangent square of theta will equal cosecant theta times cotangent theta. Okay? That's what it is. But allow me not to show the reason why I want you, as my calculus students, to verify this on your own right here, okay, to get yourself convinced. But now since I'm saying that this will be equal, so in my next step, the secant theta over tangent square theta can be written as the integral of that, okay? And so now I'm going to erase this result. All right, so now in my next step, we're looking at a 1 over 16, that constant coefficient there is still there. And so now integral of cosecant theta times cotangent theta with a d theta. Okay, all right. And so now in that way, what do we recognize here? Sweet, cosecant theta times cotangent theta. Isn't that this is the derivative, because we're taking antiderivative right now. So think closely with the derivatives you have learned back in your calculus 1, in your differential calculus. But isn't this derivative, or at least the opposite of the derivative of cosecant function? Okay, and so but here derivative of cosecant function is a negative cosecant times cotangent. Here we have a positive one, so that means the final answer here has to be minus 1 over 16 times cosecant theta. Okay, and now it's plus c. It's simply just that, minus 1 over 16 times cosecant theta plus c. Okay, so the answer now is pretty straightforward, but now we cannot stop here as our real final answer. We got it done. We're taking the antiderivative, but we got to find our way to bring back the expression here in terms of x right here, our final answer here in terms of x. Okay, so let's have another look at our earlier substitutions that we made. So x here equals 4 tangent theta. And so I came up with that deriving work right here. Tangent theta, on the other hand, must be equal to x over 4, consequently. So now we can put all that information on a right triangle. Okay, and like I said, aside from your right angle, that anywhere you're putting it, then any of the other two vertices, that's where you can put your theta. So I decided to put my theta here, just a personal choice. But now tangent theta equals x over 4. And we know famously that tangent is defined as tangent for any angle theta in a triangle, in a right triangle, is defined as opposite over adjacent, opposite over adjacent. So that means if I'm placing my theta here, then it's x over 4, opposite over adjacent. That's how we can have our, that's how it should be consistent with tangent theta is known to be x over 4. And then in that case, since this is a right triangle setting, then the hypotenuse here must be x squared plus 16 inside the square root. Okay, and so cosecant as a trigonometry definition, it's 1 over sine function, 1 over sine function. But it means it's the reciprocal. So as a more in-depth understanding, it's cosecant is the reciprocal of sine function. So sine function is a opposite over hypotenuse. But now reciprocal of sine function means we're looking at hypotenuse over opposite, hypotenuse over opposite. Okay, so that means I think my space here is a little too small, so let me jump to the other board and write that down. Write down that quick little note right here. So cosecant of theta in that triangle that we are seeing, cosecant of theta must be, in this case right here, hypotenuse over opposite. So it has to be the square root of x squared plus 16 over x. That's how I'm seeing hypotenuse over opposite. Okay, so now we are ready. So with our final antiderivative currently expressed in terms of theta, cosecant, and we found out all that. So 1 minus 1 over 16. Cosecant now is square root of x squared plus 16 over opposite x plus c. The problem is surprisingly simple. We are done, ladies and gentlemen. Okay, you can rewrite this. Technically, you're done here. And I believe and pretty much any instructor is going to be okay with this final form of yours right here. But you can also optionally rewrite this as square root of x squared plus 16 over, it's a minus actually, minus, and over 16x squared, in case your teacher prefers, in case your professor prefers putting that all in one fraction right there, instead of separating out this coefficient right there. But that is our final answer for this. Okay, and so that's how we're done with the first problem in our example 2 right here. So again, see, it's not exactly like that the promoting problem, that problem I brought up in the introduction about the tangent theta substitution, but it still has that part right here where I was mentioning the square root of a constant term plus an x squared expression right there. Okay, plus with a square variable expression. Okay, but even though here it's kind of all over and it has an x squared in the denominator together with that. All right, so let's now look at part B of the same example 2 over here. All right, so for part B, what I have here, let's look at the integral of simply 1 over square root of x squared plus 4, okay, the dx. Okay, and let me tell you, this one is actually simpler. It's even shorter than the one that we have done previously in part A right here. So it's just more experience, more repeated experience right here. So now I see square root of x squared plus 4 recognized. And the point now is, see, we recognize that generality exists here in this problem. We have a square root expression. And inside of that root, we have an addition between a square term, a variable square term, and a constant term. And further, that constant term here can be regarded as a as a square of another number. Okay, that constant can always be expressed as a square of another number over here. Okay, so now once we realize that nature about our integral function, but it's not exactly like the problem I put in the introduction. Here it's actually 1 over that square root expression. So now here's our substitution. I'm going to let x equals, so this 4 right here, regarding that as the square of a number, then it's going to have to be square of 2. So I'll take that 2 right here. So x equals 2 tangent theta, under that requirement that the theta has to be anywhere from minus pi over 2 to positive pi over 2. All right, and so now from that substitution definition, then I can see that consequently x over 2 must equal tangent theta. So we come to another point, another expression, another equality that's useful for some of our later substitution. So now, but right from that, we see this x here as a function of theta. So we can take dx d theta, the derivative of the function x in terms of theta here. And that equals 2 times secant square of theta. And again, just like how I have explained many times, now we are seeing this not only as a notation for derivative, but also a ratio of 2 differential expressions, dx and d theta. So in that way, I can multiply the d theta expression to the other side of our equation currently. So that means I'm going to produce a dx equals 2 times secant square theta times d theta. Okay, and this will be later on useful for our expression as well. So now, here we go. I am ready for putting all the substitution little steps together in place. All right, so the integral, I did not have anything to substitute for 1, so it stays there. The square root in the denominator now becomes, here's what it becomes here. X squared is now, x is substituted by 2 times tangent theta. So x squared has to be 4 times tangent square theta. Okay, and then we're going to add with the other 4. And then dx here must be, it's a multiply, so dx here must be multiplied with 2 times, or substituted by 2 times secant square of theta with a d theta expression. Okay, and so now this 2 can be brought in front as a coefficient, and just like how I did in example part A right there, in example 2 part A, why not leaving the secant square in that numerator to keep our expression shorter. So it's 2, and then there's the integral. We have secant squared of theta. Okay, and over now in the denominator, in the meanwhile, I can also factor out that common factor 4 here. So square root of 4 times tangent square of theta plus 1 inside the root, and then there's d theta. Okay, so we keep getting closer and closer to the next step right here. So how about I have enough space to write one more step right here. You can see that we can pull out that 4 in this denominator square root right here. So I'm going to pull out that 4, but pulling that out from the square root, it's going to become a 2. And so it will cancel with that 2. So my next step really is we don't have that 2 any longer. And then we have secant square in the numerator divided by square root expression of tangent square, okay, theta plus 1. All right, so my writing is getting a little tight right here, but it's still viewable for anyone. Okay, so that's how I reduce in my next step right here. All right. Now onto my other board right here. So from our previous step, here we are going to look at, so secant square theta divided by, now the square root expression there will become, so again, just that. 1 plus tangent square or tangent square plus 1 will equal secant square. Okay, just that reminder. And so now the expression inside the square root right here, let's have a look again at so it's, the denominator here has square root of tangent square plus 1. The square root of tangent square plus 1. But tangent square plus 1, just now I reminded that tangent square plus 1 has to equal secant square. So on my other board right there, I'm looking at inside of the square root, I'm looking at, we have another secant square in here. Okay, another secant square. So taking square root of secant square theta will equal, so secant square theta divided by just secant of theta. Okay, just secant of theta. And that means we can reduce this even further, simplify secant square with secant. So that gives me an integral of simply secant of theta with a d theta. This is one very basic integral problem right here, and you have seen that we have had this problem earlier where it's just simply the secant of theta. So now you can search in any textbook or look at my other video lessons, just short video lessons showing how to find the integral of secant theta, or there are tons of video lessons over the web right there where you can find the integral, people showing how to find integral of secant theta. There, you know, I have my own angle of approaching this problem, but other people have other angles of approaching the problem. But in the end, secant of theta, integral of secant of theta becomes the logarithm of secant of x, or actually it's not secant of x, secant of theta plus tangent of theta, okay, and plus c. All right, logarithm of secant of theta plus tangent of theta, and of course we're putting that in absolute value. Okay, so this is at least our answer for the antiderivative. We have found the antiderivative. Okay, we have found the indefinite integral. But then we can't just stop here because our final answer currently is in terms of the theta variable, which is not what we desire from the beginning. So here we need to find our way to re-express this in terms of x right there. Okay, so now again I'm going to swing back to my other board and let's investigate further our substitution right here. So just from that right here that I pointed out, and very similar to how I have done that throughout earlier problems, we're now going to put our relationship between tangent theta and x and 2 here on a triangle. Okay, and so how about here, this time I have enough space, so let me draw the triangle out this way. Okay, and the right angle is here. So aside from that right angle, any of the two remaining vertices, I can put my angle theta there. So I decide to put theta here. So tangent of theta is defined to be opposite over the adjacent. So that means x is here and 2 is here because this is opposite of my angle theta. I decided, recall I decided to put my theta here. So opposite over adjacent. Okay, and so that means hypotenuse here has to be the square root, according to Pythagorean theorem, the square root of x squared plus 4. That's hypotenuse right there. So that implies that secant of theta, again, secant of theta is the reciprocal of cosine. Cosine is adjacent over hypotenuse, but now secant is the reciprocal. And so that means now we're looking at the hypotenuse over the adjacent. So square root of x squared plus 4 over 2 right here. That's how I can see it. That's how I can calculate secant of theta in this triangle right here. Again, secant is the opposite, is the reciprocal of cosine. Okay, and cosine itself is always known to be adjacent over hypotenuse. So that's why in a triangle like this, secant of theta is hypotenuse over adjacent. Okay, and so now in that way, I'm ready for bringing our expression in terms of x back into this final answer right here. So it's natural log of, so secant of theta, just now on my other board, I found that to be square root of x squared plus 4 over 2, and I'm adding that with, so now with my other one right there, tangent, we saw that on the other board, x over 2, okay, and plus c, x over 2 plus c. All right, and so in that way right here, you see we can write all this here together as a, so now allow me to erase the step right here because I want to again remind people, even though you have seen this in the earlier problem, but we want to even simplify further in case your instructor doesn't like this, right? In case your instructor requires more than that, then we can have even the better way to simplify all the way to all the way down right here. So I'm going to combine these two as one fraction right here because they have common denominator 2. So it's natural log in absolute value x, square root of x squared plus 4 plus x, that's the numerator, and all over 2 plus c. Okay, but now we recognize that this is a logarithm of a quotient, top and bottom right here. So I am going to rewrite this as natural log of the square root x squared plus 4 plus x. Okay, and I'm subtracting the natural log of 2, absolute value of 2, and plus c. Okay, and plus c. But just now, just like how we have seen that in the earlier problem, then this natural log of 2, this minus natural log of 2 is a constant. So this can be included together with that other constant c to make a different constant c. So that's why in that case right here, I no longer need to write the minus natural log of 2 plus c, but I can just write that as a different c. For real careful purpose, c1 in the end. C1 or C, or just if you're using the same letter C again, nobody is gonna be hurting you for that. Okay, you still, what I mean, you still have your legal right to still reuse the same C as well, because it's the point. It's just any constant. Okay, and so now that's your final answer right here. Very simplified version of your final answer. Okay, so that's how we're done with part B of our example. All right, and so I prepare in my lecture notes for this example one more problem right here. So let's look at part C. All right, so now our example in part C right here. Let's look at, how about we're looking at an integral of 1 over, and here I have the square root of x squared minus 2x plus 10, okay, dx. So this problem, it looks threatening at first, simply because we're completely out of that usual understanding that we have an x squared plus an a squared. We're completely outside of that world here. We have a magical x term between our two x squared term and the constant term right here, and that's the part where it's bringing a threatening sign here. Okay, but no worries. So this is how, again, I keep bringing up these problems so that to convince anyone learning with me that you cannot get away from the algebra. You gotta get your algebra going. The stronger you are in your algebra background. Okay, the better it is, the smoother it is for you to move on in any of your higher math courses right there. Okay, and you see, you don't have to. that's why there's this video lesson right here. At this point, I'm not expecting you to be the master at algebra in everything and all that, but you have your lifetime to always keep working on your algebra right here. So in the way how I see this, yes, admittedly, it's not clear to see the x squared plus a constant term inside the square root, but I'm going to use complete the square methods right here, okay, to do the following. So how about x squared minus 2x, a little bit review of algebra right here, plus 10. I'm going to purposely write that 10, that constant 10 a little too far out right here. So at least I group out the same expression here, but I group out and without worrying about signs at all, just group out whatever the sign is, group out the x squared term and the x term together, okay, and then the plus 10. And so, let me write that I want to leave a little space here. So now inside of the parentheses here, then we're going to have the two terms here, but I leave a space here because I want to produce. So here, this is b, that minus 2 is b, and then the constant coefficient with the x squared here is a 1. So I'm going to create a magic number. A magic number. This is how I interpret it. This is how I interpret that to my algebra students. So when I teach my algebra student, I call that the following is a magic number over here. Minus 2 is from that b right here. I'm going to divide by 2 times. So it's a formula, 2 times 1. So 1 here is the coefficient a in front of our x squared. Isn't it always clear that ax squared plus bx is the standard form for, plus c is the standard form for a quadratic? So this is an almost complete. We isolated out that beginning 10 right there, that beginning c. But we're looking at b and a right there. So b is here, the coefficient with the x, and a is the coefficient with the x squared. And then I produce that magic number. So the magic setup for that magic number is b over 2a. That's what I'm doing. And then we're going to actually have to square that. All right. So I'm squaring that. So minus 2 over 2 times 1 is just simply a negative 1. But negative 1 being squared is a positive 1. So this is what I'm doing. So once I found that magic number, I am going to put that magic number inside of my, in that empty space here, inside of the parentheses. But I'm putting that as a plus 1. Okay, that's the magic number. But if I plus anything, just the rule of algebra, anytime we add anything, we have to make sure we subtract that away to maintain the exact same problem from the beginning. So if I decided to plus 1, if I go with plus 1 and y plus 1, again, it's that magic number. That's why I call it magic. Okay? Then I have to subtract 1 away. And so now, once I did that algebra trick right there, and see, this is just an interpretation of how, keeping it understandable for people. But if you're already fluent with your complete the square method, this is not the only way. This is not the only way to explain. Okay, so you don't have to stick with my way. Just complete the square is the point. And so now, here's how I'm seeing this. Okay, I'm gonna bring that negative 1 outside. So my parentheses is now gonna regroup. I'm gonna regroup this part right here inside my parentheses. I'm gonna regroup as following: x squared minus 2x together with that plus 1 is now one group. I'm leaving that minus 1 guy outside. So that minus 1 together with the 10 become a different constant. Okay, so now I'm looking at x squared minus 2x plus 1 as one group, but plus 9. Okay, so much beating around the bush. But now, so somebody else, you can see, if you are fast at your complete the squares, you can see the 10 here can be quickly split as a 1 plus 9. That's a different way of seeing it. So this is just, I'm trying to use probably a little longer, but it's solid for anyone who's still a little shaky, who's still not too comfortable with algebra right here. But now, what am I trying to do over here? The part that I'm having, that I now group in parentheses here, I have a perfect square. That's what I meant by complete the square, because right after this point grouping it, we didn't have a perfect square yet. But now producing that magic number and taking it away, right, and then and regrouping it, now I have a perfect square here in my group. And then the other guys being added together, combined together with 10. So my point now is that the x squared minus 2x plus 1 can be rewritten as, all this here can be rewritten as x minus 1 all square plus 9. Okay, let's see how useful that is. So my integral gives me the following. So after so much algebra explanation, here I'm looking at 1 over square root of x minus 1 all squared plus 9 with a dx. Okay, so now, ladies and gentlemen, have some good thought about this. Have some good thought about this. So back to what I was pointing out earlier about the generality. You see, the point now is that anytime that you're doing your tangent substitution, x equals a value times tangent. Well, of course, 9 here is a 3 square. That's your a right there, right? But you see, in your a squared plus x squared formula here, this is not, it's intended to be not only a single variable x to be squared, but it can also be understood as an expression, like I said earlier, a variable expression square. That's the idea. This is what it is. This is a variable expression being squared. Okay, so now in that observation, and of course, again, the 9 here is a 3 square, so your a is here. A is a 3. All right, so now I'm ready for making my substitution. This time I am going to substitute x minus 1, the whole x minus 1, the entire variable expression. I'm going to substitute that away because that's what I recognize being the square form. Okay, and that's why we were doing the complete the square. And so now this is tangent. I'm going to let that equal to 3 times tangent of theta. 3 times tangent of theta. And so, and of course, allow me to start skipping that requirement. So we know in the back of our mind that it's got to be theta anywhere from minus pi over 2 to pi over 2. I'm not going to write it here anymore. Okay. So now, consequently, this relationship here can be turned into x minus 1 over 3 to equals tangent theta. That's for a later purpose right there. Okay. But now from this relationship, from this important relationship that we chose, then that also means x equal 1 plus 3 tangent theta as a function x in terms of theta. And so now I can go ahead and take the derivative dx d theta. And so from your experience taking derivative at this point in your learning calculus, derivative of 1 is 0. So really you have 3 times secant square of theta. Just like that. Okay? So it's just a simple derivative problem. And again, seeing this notation here not only as a notation but also as a fraction, as a ratio of two differentials dx over d theta, then I can do dx equal, because now I can multiply that d theta to the other side. So dx equals 3 times secant squared of theta times with the d theta differential. Okay, so now we are so ready to do that substitution. So it's an integral 1 over, okay, and then I have here, see, square, I mean that inside of my square root, that x minus 1 all squared there can be written as 3 times tangent of theta all squared, so 9 times tangent squared theta. It's substituted for all that, x minus 1 all squared, and I'm going to plus 9, okay, and then the dx right here can be regarded as, dx can be substituted by 3 secant square theta. So times 3 secant square, okay, but okay, 3 secant square theta and d theta. Okay, all right. And so now since we're still having enough space right here, allow me to write the next step down here. I'm going to write that 3 secant square, and there's a 3 as a constant coefficient. I'm going to keep it in front. Okay, and then the secant square of theta. And then there is a square root in the denominator. So now in this step right here, allow me to factor out the common factor 9 among my two terms inside the square root at the denominator. So here it's 9 times, and then tangent square theta plus 1. Okay, and with the d theta. Okay, so and then so in the next step, you can see that I can go ahead and pull the 9 outside of the square root. So this problem in part C really proceeds very similar, okay, almost like over 90% similarity right there. It's just instead of having a single x here, we're having an x minus 1, a variable expression. Okay, so let me move on to my other board right there. And so now we can start picking up pace a little bit as well. So in my next step, we have 3. The integral now has secant square of theta, And then in the denominator, as I was saying in the earlier step, we're going to factor out, and we already factored out the 9, but we're now going to pull it outside of the square root. So that will become a 3, but okay, so it's 3 times square root of tangent square of theta plus 1 with a d theta. Okay, just one little step so that it's still connected with the other board. So now the 3 here cancel with that 3. Okay, so our integral really becomes just one simple one like this. Okay, the factor 3 is completely gone. All right, and so now just that same reminder, 1 plus tangent square of theta, will famously known as equal to secant square of theta. Okay, nail down that result right there, that trig identity. So see, back in your days, it's the way how learning math is. Back in the days back in those days, you were learning about trig, where we were first introduced to these. Gosh, it seems hopeless to try to memorize these things. Okay, but now in these days, when you're actually sitting in a calculus course right here, then all of those experiences will come back and pay for all that time that you had, such a painful experience back then. Okay, but now it's become handy for us. Okay, so it's my advice for anyone, maybe you face a challenge here, but it will become a good payback for your future course. All right, so now that becomes so we got secant squared of theta, and then we divide it by so very like a part B that I did. And so now it's going to reduce down to a secant of theta, simply because all that here is a secant square. Taking the square root of secant square gives me secant of theta. Think as closely as possible to the part we have done back in part B of the example, whereas we're right now at part C. So I'm going to cancel out the secant here, cancel the secant. That gives me just secant of theta, d theta. Okay, so now we know from the earlier work right there, very similar to that. So here the answer to that antiderivative or indefinite integral has to be the natural log of secant theta plus tangent theta plus c. Okay, and so now we have to bring back our expression in terms of x. And so now just like that, so allow me to swing back to the other board and give some interpretation right here. So it's slightly different with the problem in part B in a way that, so now I'm going to put the triangle here. Okay, and let's call that the right triangle. And I decide to put my angle theta here, even though you can also put it here. But know that anywhere you put your theta, this is opposite side, this is adjacent, and that's hypotenuse right here. So tangent is, this time in this problem, x minus 1 over 3. And tangent is opposite over adjacent. So that means I have to put my x minus 1 here for that length right there. And 3 is here. Okay, but then that means the hypotenuse here has to be that square root expression minus, x minus 1 all square plus 9. That's the hypotenuse. So in that way, that's how we got tangent. Okay, so we can use this to substitute that into the tangent expression on my other board. But then further, again, very similar argument that I've made back in part B right here. Secant is defined as the reciprocal of cosine. Okay, but cosine on its own is adjacent over hypotenuse. So now secant means we're looking at hypotenuse over adjacent. So that means secant of theta here has to equal the square root expression, x minus 1 all square plus 9. That's hypotenuse over adjacent, 3. Now I have all information I need to substitute back into our current answer on this board right here. So now I'm looking at natural log of, here's my square root expression, and x minus 1 all square plus 9. Okay, that's over 3. That's secant of theta. Okay, plus, and now tangent is just simply x minus 1 over 3. Okay, plus c. All right. And so, yes, just like that, I'm going to proceed further to simplify this expression. There, it should be about 70% of instructors out there or professors out there who are okay with students leaving the final answer like this. But in case in case your professor is among the other 30% who prefer you to, who would like to see, who requires you to simplify this further, then you can go to combining this into one fraction. So it's logarithm of the See, square root expression x minus 1 all square plus 1. Now, I'm running out of space myself here, so allow me to actually use this space above. Okay. All right, so now I'm looking at logarithm of the square root expression x minus 1 all square plus 9. Okay, but I'm adding with all that x minus 1, and I don't think I need the parentheses here, and all of that here is over 3. Okay, all of that is over 3, and then plus c, the constants. Okay, and so you have seen this often enough now at this point, or frequently enough now, and so I'm going to write this as logarithm of square root of x minus 1 all square plus 9. You also have your choice of writing this in the beginning form as an x squared minus 2x plus 10. Okay, because this is now the final answer, so you can bring it back to the beginning form as well. But now plus x outside of the expression minus 1, and then minus a logarithm of 3 in absolute value plus c. Okay, but then just like that same argument I've made multiple times earlier, we can include this, now realized as a constant. We can also include that together with that c from the previous step to make a different c. Okay, so for careful purpose, I'm writing that as a c1, but if you're writing that just as a c, nobody have the right to take points off for you on things like that. Okay, so just that's your final answer. Just realize that it's going to be a different c from the previous one, but like I said, if you're using c here, you should be fine. Okay, but that's how we're done with our problem here in part C of our example 2 like that.